I am Nicolas Quereau, working at Explore France, and I will be presenting the work that we did jointly with the CEA list laboratory in France on the paper called Towards Privacy Preserving Platooning Services by Means of Homomorphic Encryption. So first, I will be describing platooning, then homomorphic encryption, and the application of homomorphic encryption to platooning services. So the platooning technology is a technology developed for automatic vehicle tracking, so towards autonomous driving. So the idea is to have a leading vehicle which can be followed automatically by several vehicles. So this is easier to implement than fully autonomous driving. Platooning relies on V2X communications and sensors and cameras. So the main focus of this paper is to make the truck drivers benefit from the platooning technology, so that any truck driver could follow another truck instead of resting on the somewhere. It could be still driving towards its destination. So, for example, let's say you have a user or a candidate on the road, and it would like to follow a platoon nearby. What it would do, it would send its location and its destination, for example, to a server, and the server could make him in a connection with a platoon nearby, so that the user can follow this platoon and reach him somewhere. The problem is that the server needs to have access to the client's sensitive location data. And our idea was to use homomorphic encryption to privately connect the user with the platoon. So to tell you about homomorphic encryption, I recall to you how cryptography works, usual cryptography works nowadays. So if a user wants to send some data to a server and the server wants to perform some operations over the client's data, what the user can do right now, it can send encrypted data, but the server has to decrypt the data in order to perform some operations over the data from the user. And then it gets sent back the results in an encrypted form. But the problem is that the server needs to access this data. And homomorphic encryption aims at preventing this decryption state on server side and to only use encrypted data at all points. So the first example would be a search engine over a server where the user could send an encryption of its query, and the server could give a result to the client without accessing the data inside the query. So it would only use the encrypted data and still be able to send back an encrypted result. This way, the server doesn't have to read what the user was asking for, and the user would still be able to obtain its answer. So we wanted to use homomorphic encryption in order to create a platooning service while maintaining privacy from the user's data. So what we do is we encrypt the data from the client homomorphically in our protocol, but the server here has access to the platoon's data. For example, if the server would be having some platoons which would agree to share some data with the server, namely their positional data. But the users, they would like to stay private and not to share any data with the server. So we assume that after that the server returns the platoon number that the user would have to reach, the user is able to privately know how to contact the platoon, for example, with low range communication or some privacy preserving mechanism that can be up to the choice of the implementation. So as I said, the server disposes of a non-encrypted database with the platoon informations, and instead of disclosing the position of the client to the server directly, what we do is we make the client perform a PIR query to the server. And the peer query principle, which I will describe to you just after, means that someone with a peer query can obtain a precise element of the database without disclosing to the server which element it wants to obtain. And instead of disclosing the precise position from the client in its destination, what we do is we estimate the future locations of the platoons. For example, the platoon has a fixed, or any user on the road normally knows that in 10 minutes it should be in like the road A5 segment 10, let's say. So we give to the server, the platoons give to the server an estimation of its future location. And what the client does, it performs a peer query over this estimation. Let's say the user will ask to the server who will be in the same segment as him in 10 minutes. And the server with the peer query will return to him this precise set of platoons privately. So to perform a peer query, what we do is we send encryptions of zeros everywhere. So for example, in this array, you have zeros non-encrypted here, but they will be encrypted homomorphically, except for one precise element, which will be a 1. And then when you perform a multiplication between this ciphertext and the database from the server, the output will be encryptions of zeros everywhere, because 0 times anything is 0. And one element which will be non-null, which is the element which is set to 1 from the client. Of course, this array is encrypted, so the server cannot see which element is 1 and which one is 0. So, as I said, the client first encrypts the estimated future location where it would like to meet a platoon and sends it to the server. The server performs the PRO query by multiplying the ciphertext with its database, and then it sends the result back to the client. Then the client obtains a set of platoons, which encodes both the ID from the platoon and its destination. And with this set, the client is able to know whether there is a platoon that's interesting him at the target location. So for the PIR query, we use the homomorphic encryption scheme. We could use any additively homomorphic encryption scheme to do that, but we use BFV because it allows for efficient SIMD operations thanks to batching. And also it induces a natural multi-user management without requiring to share any homomorphic public key on the server from any client. So that's pretty convenient. What we do with the parameters we have, we could encode about 8,000 numbers of each 60 bits. And we define in the paper how exactly we encode the sets of platoons and how how we can obtain the desired queries. Note that BFV, which is a homomorphic encryption scheme, can be replaced by BGV or CKKS, which are two other homomorphic encryption schemes, which allow them also for batching. So in terms of performance, the most interesting number is the 2 milliseconds of server computation, which allow for about 500 queries per second on a single core, which can obviously increase a lot with better resources. And the size of the ciphertext can be pretty high. It's around 450 kilobytes, go and return. So that's probably the biggest cost in our protocol. We also propose a probabilistic tool to prevent a user from extracting the database during a PIR query, because in a PIR query, because the data is encrypted, the server cannot know whether the data was set to 0 everywhere except for one precise location. So we propose a probabilistic tool to prevent the user from setting once everywhere and thus extracting the database during the PIR query. Also, some inference attacks can still be possible because the query is encrypted, but the database with the platoon is not. And then if a user performs a query, let's say at midnight, maybe 10 minutes after, the platoon database will be updated for one precise platoon, and then the server could know that the user who made the query asked for this precise platoon or joined it. So this kind of attacks need to be handled carefully, and it can be prevented by encrypting the platoon database. However, the performances will go down and the natural key management will disappear. So we believe we achieved scalable computational performances to link users with platoons while preserving users' location privacy. And we have natural multi-key management. However, we still need to be careful for the platoon inference attacks, which could leak some information about the user. So, thank you for your time. If you have any questions, feel free to reach me.